Okie dokie, maybe we can get started. Welcome to our first Monday seminar for 2025. It's really wonderful to have Ian Moult here, who's normally at Yale, but is sacrificing a week in the California sun to be in lovely central New Jersey on the as February approaches. Ian will be here for the week. He was here 4 years ago, I think, when you just started thinking about energy correlators, and he's written a sequence of fascinating papers over the last 4 years. So I think it's a great time to get an update on this extremely interesting subject. Take it away, Ian. Oh, we will be taking him to a dinner at around 6. So anyone who wants to go, please let me know, and we'll gather in the lobby. Let's say we'll gather in the lobby around 6. Take it away.
Perfect. Yeah. So thank you very much for the opportunity to speak and to visit. It's always fun to talk to everyone here. As Anima said, so today I'm going to be talking about some progress in trying to understand a particular class of asymptotic observables, which are these correlation functions of detector operators, which kind of go colloquially under this name of energy correlators. And so these things have kind of long been known as kind of model or kind of theoretical abstraction of what is done in collider experiments. And so one thing which has really changed in the last kind of year or so is that they've now become a real kind of practical tool, which is used in all the major collider experiments to actually get out standard model physics. And so one of the nice things is that once they're experimentally practical, the experimentalists can devote a lot of time to kind of measuring other things, which are kind of tangential to them, but are more interesting to us. And so they've now been able to measure a lot of these, just kind of, for example, higher point energy correlators, which we kind of like on the theory side, because as I'll describe, have some nice analytic structure. And so there's been this nice kind of interplay between kind of trying to push the boundaries of the theory understanding of these objects and what has been, or what one can actually measure in experiments. And so what I wanted to do today is just to kind of go through and first give a fairly kind of elementary introduction just to kind of the physics of what these energy correlators are trying to probe, just at a very physics level, comparing kind of how they behave in conformal field theories and QCD, just to give some intuition for their behavior. If you see, for example, an experimental plot, kind of what it's telling you. Then I'll discuss a bit kind of what is known in their calculation, what is known about their analytic structure, and kind of what the open or what has been achieved and what the open questions are. And then I'll show just some nice experimental plots at the end of what the experimentalists have been doing. But just to begin with some kind of very big picture of motivation, just so that we're all on the same page. So as an experimentalist, what one does is one has some kind of collider system where you have a whole bunch of stuff coming out. And so the experimentalist sits off at infinity. And what they want to do is to try and understand the kind of microscopic dynamics of what's going on. And so one very concrete thing which they can do is to measure correlation functions of certain detector operators which live at infinity. And so they can do this for a lot of different detectors. And so I'll just write these kind of generically as some D at some particular theta. And so you can think of this concretely as measuring some energy flux. So this is some particular example, but of course they can measure many other things, and depending on time, I may talk about that. So this could also be charge or whatever favorite property you have, even something more exotic like strangeness. And so they can measure kind of correlation functions of these objects. And so what the experimentalist then kind of has is some list or some functions for some particular state that they want to study, which are just some functions of the kinematics on the sphere. So these are some functions of these angles, and so these are just expectation values in some particular state, which you produce in your collider of a bunch of these detector operators. And so these are just some functions of the kinematics on the celestial sphere, and they in some way encode or kind of characterize this state through the fluxes which are coming out to infinity. And so as an experimentalist, or kind of what motivates one to study this, is first, as I said, for just very, very practical reasons. What you'd really like to be able to do is to have a map between these functions on the sphere and the kind of microscopic properties of your theory that you may want to understand. So what you want is the kind of sharpest map possible between these set of functions and the parameters of your underlying theory. And so just, for example, for very concreteness, you might want to measure some kind of couplings in your underlying theory, or some masses or something, or if you produce some more, I don't know, complicated collision in the middle, so you can have some like quark gluon plasma or something that you produce, you might want to measure some for example, transport coefficients or anything you might want to think about. What you want to do is to understand how those manifest in these things. And in particular, a lot of where the progress has been is in really kind of clarifying this map, because if you can identify, or if you understand very well the properties of these objects, and you can very or easily identify how some of these features manifest, then it makes it very easy in an experiment to kind of pick out from what you measure certain properties. And if you want to, for example, measure something, that kind of clarifies the map. And then the second obvious motivation is there's been a huge amount of progress in understanding the analytic structure of, for example, scattering amplitudes, cosmological wave function, cosmological correlators. And so this is another nice physical observable which one can measure. And so we'd just like to understand better the structure of physical observables. I think this could be both at the kind of high picture level of understanding how things like causality and unitarity kind of manifest in this, but also just at a much more kind of lowbrow level of just understanding, if I compute these in perturbation theory, what is the structure of singularities, what are the special functions that appear, and even just how do I efficiently compute this in perturbation theory. And so what I wanted to do today, as I said, is just kind of give an overview of this. So this is a brief kind of outline of the different things that I wanted to talk about. So first, I wanted to take the kind of simplest, non-trivial example of this, and to go through in detail the specific case of this 2-point energy correlator. And just kind of go through how it behaves. So first of all, how you actually compute it, how it behaves in some different theories, and then ultimately what it looks like in kind of QCD. And so this will give intuition for the kind of plots I show, and also just some basic kind of background on how you actually deal with these types of observables. Then I'm going to talk about higher point functions. So as you can kind of see from this picture, these are functions of the kind of kinematics on the sphere. So they become interesting if you're interested in studying their analytic structure, only once you go to higher points, so kind of 3 and beyond. So we'll discuss a little bit of kind of what is known about these higher point functions, and just some kind of observations about their analytic structure, and then discuss some things which would be could be improved in this understanding. Then we'll discuss a little bit the extension of these things to gravity. So we computed a few of these objects, in particular this 2- and 3-point correlation function in supergravity, where they also exhibit kind of a nice structure. And I'll just discuss a little bit about that. Again, it'll just be some kind of observations of what we see in perturbation theory. And then I'll conclude by showing some nice experimental plots. We can hopefully end with some nice pictures. So any questions before I continue? Okay. Okay. So the first thing I wanted to do is just go through in detail this 2-point correlation function. Again, just to try to give an example of what the physics is actually probing. And so this is what is referred to as this energy correlator. And this will be the specific case where this detector that I'm measuring is just measuring the energy through some particular angle. And so in particular, the object which I want to discuss the properties of is this 2-point function. And just for simplicity, we can do it in some simple local state. So this object, and I'll just assume that it's some kind of strictly symmetric state. So this is a function of one variable. So it's a function of this variable which is called z, which is just the angle between the two detectors. And so this object is something referred to as EEC, or energy correlator, which is a function of z, and it's not conformal of the scale of the problem. And so what we'd like to do is to just kind of understand what physics actually is imprinted in this object. And so this object in general is a function in the physical region, plotted as a function of z, which will go between 1 and 0. And so in this region 1, it's when these two detectors are exactly back to back. They have 5 between the two detectors. And at this end down here is when the two detectors have 0 angle or between them. So it's as this theta goes to 0. And so what we want to understand is kind of for different states and different theories, what this actual plot looks like. And so to get some intuition, we can first just go through the kind of 2 different ways that one can actually compute this thing. And so one thing that's nice about this object is there's kind of 2 views that one can take. One is a kind of correlator perspective, and one is a kind of amplitudes or on-shell perspective. And so they're both useful for getting some intuition for the behavior. And so just as a recall, so one can actually write down an operator definition of this detector operator, which is measuring the energy flux at some given angle. So one can write it as this kind of limit of a particular integral. Of this. And so this allows you to go from the stress tensor of your theory to this detector object. I've sort of written this in a non-covariant form, but you can also, if you're in a CFT, you can just directly move this to infinity and just write it as a null integral. And you can easily check. So the other way, which is nice of thinking about this, is to think about its action on some on-shell or some asymptotic state. So if I just have a whole bunch of free particles coming off to infinity with some momentum or a whole bunch of momentum k, this has a very simple action on those on-shell states. So this is just the sum over all the particles in my state. So it just acts or just picks up their energy. And then that's localized on a particular solid angle. And so it's easy to take, for example, you can just write this in terms of creation and annihilation operators, and really just, it's a kind of Peskin level problem, just act with this on some asymptotic states, and you'll see that you get this out. And so this, you can see it really does, as you'd expect for a kind of passive detector, that really just waits by the particular energy like that.
How does the tau integral start at 0 instead of minus infinity?
So here if we're just inserting some local source at 0, then you can just do it from 0 to infinity. So I'm imagining I can kind of place my operator insertion at 0, and then I just have this flux at future null infinity.
Well, I'm confused about whether future null infinity would go. Okay.
So using this, there's kind of 2 ways of computing these particular objects. So the first is if you happen to have, so there's kind of the correlator approach. So if you happen to have a whole bunch of endpoint functions of your stress tensors available, then you can just take these correlators of local objects and perform these integrals. And this will compute for you these energy correlator observables. And so there's efficient ways of actually doing this, but for now, I'll just kind of leave it like this because I won't really use that. And so this has been used mostly in n equals 4, where you can reduce these to 4-point operators of scalars, and these are very well known. And this also hasn't really extended beyond because you don't have typically 5 and higher point functions. So this has mostly been used just to compute these 2-point function or 2-point energy correlators in n equals 4. And so essentially, if you have n plus 2 correlators of local operators, you can get the n-point energy correlator. In some sense, this is telling you a lot that a lot of the physics of the 4-point function is encoded in these energy correlators. And so the second way is to use the kind of amplitudes or on-shell approach of just sticking in some complete set of asymptotic states here and here. And so if you do so, what you find is that what you need to do is you can write this as an integral over some It's a very phase space. Of a form factor for your O into kind of n particles, the squared form factor, and then you just have to sum over all the possible states. And so then the only thing you have to do is you have to constrain the phase space that you integrate over by these delta functions shown here. So you can kind of draw this pictorially. Is if you have some form factor, it's squared. And then at the cut, you have to put these weights. And so if you're measuring just the 2-point function, you essentially just insert weights of the energy, for example, at 2 points, and a delta function that constrains the angle between them. And so you put a kind of measure. This, and you'd sum also over all the different pairs. And so this would give you this energy correlator as a function Z. And so this gives kind of a very perturbative way of computing these objects, and this is the one that has been pushed to higher orders or higher points as well as higher orders in QCD. And it also relates it nicely to a lot of these objects, which there's a lot of perturbative data for. So you can really kind of repurpose these to do these types of integrals.
About the first approach, maybe.
Yeah.
How much of the 4-point function we need to know? Like, we can truncate some conformal block expansion. What is known about this?
Good. So this is a good question, which I think hasn't been. So there's a pretty efficient way of obtaining this, which is given by Korchemsky and Sasha Zhabotev and Cayenne and maybe some other people. What you actually need to do is to take some certain set of discontinuities of the 4-point function. So you know that this object is going to be much simpler than the full 4-point off-shell function, but at the current level, there's no kind of direct prescription for computing those discontinuities. So right now it's kind of an algorithmic thing where, because this thing you know to very high orders in n equals 4, and so then you take those discontinuities instead of doing these additional integrals. And so it's more a way of more efficiently mapping between that object instead of having to take more integrals. But it's not, it would be nice if one could understand exactly what information is actually needed to get this 4-point function for sure. Because it is a much simpler object than a full off-shell 4-point function. Okay.
What's the subscript of that?
Sorry.
What's the subscript of the form factor?
So this is just some form factor for some particular operator of your choice into n particles.
N particles.
And I have to sum over all n, and so this is why this is a kind of perturbative construction, and you can't do this at strong coupling, but I have to sum over all particles up to whatever perturbative order I'm giving. And this is why, so this way is very nice because you don't have any intermediate IR divergences, and so it's a kind of elegant. This way you have to regulate it and you have intermediate IR divergences because you have to sum over all the different states. But still people are pretty good at doing that. And so this way is kind of, particularly for higher points, has won out. Okay.
So I should just say again, so it's like your bomb goes off in the middle, you have all the particles coming out, you take the mod squared.
Yeah.
Just fix the directions that they're going out in and you integrate over all the.
Over everything else. Exactly. Yeah. And I'll come to some very concrete ones in a second. Yeah. But you really, I mean, that's why it's kind of nice is that you're only, so you can think, if I didn't have these here, this is just the inclusive cross section of the 2-point. And so I'm kind of weighting it with just this particular delta function. And so then in particular for these ones in QCD, I can write that delta function. I can do like reverse unitarity, and then it's just in the standard wheelhouse of loop integrals. And so that is being quite efficient for doing that. Yeah. Okay. So now I just want to say a little bit about what these look like and slowly build up towards the actual case of QCD. And so at least, and sorry if this is a bit basic, but I wanted to just go through what these look like building from a free theory to a conformal theory and then ultimately to QCD. And so again, we just have this thing which goes between z equals 1 and z equals 0. And I'm just going to start, and hopefully this will start to further address your questions with the absolute simplest thing I can do, which is just take a free theory. And I can take my source to either just be, like, I can just take a scalar, so it's 5 squared, and so my form factor is really producing just two particles coming out, or I can take the kind of other extreme behavior is I can take phi to the k, and I can take a limit where k goes to infinity. So here I have really a bomb where I have many of these things coming out. And so here is really just a geometric exercise to compute these objects. And so this one is a fun kind of exercise in doing the phase space. But this one is very simple. And so there's kind of two configurations that one can have. So on the circle, one can either have both detectors, which lie, or kind of one lies in one particle, one lies on the other particle. So that gives a delta function in this back-to-back limit. Or I have what is referred to as a contact term, where both detectors lie on the same particle, and then the other particle is just free. So in this case, it just is fixed by momentum conservation, but it's there. And so what you get is just a sum of two delta functions, one here, and one here. And so you can just write that in the free theory with phi squared, this answer is proportional to, so it's just some delta of z plus delta of 1 minus z. So the other extreme limit was this one. So here, if I just have this kind of completely essentially uniform distribution of all these things, you can guess kind of very easily. So it's nice to actually do it. And but you can guess that what the distribution will be is that it's just completely flat as a distribution like this. And so in this case, if I have this phi to the k, it's essentially, it's just a constant. If you normalize, it's kind of a half. And so these are the kind of two extreme limiting behaviors of this object. And essentially anything else will kind of lie in between. And you can think, or it's kind of intuitively nice to think of this flat behavior as being kind of uniform objects. And then these delta functions being kind of very spiky things or localized in some particular directions. And of course, this is also the behavior that you get in a lot of these. For example, if you just have this at very large coupling or in large charge states, you typically get this behavior, whereas this one is more reminiscent of perturbation theory. Okay, and so now what we can do is start moving towards more realistic theories. And so I'll first do a conformal theory and then move towards real world QCD. So the next thing we can do is a conformal gauge theory. And the fact is the gauge theory will only make a difference on one side of the plot. So if you plot this, again, from z to 0 to 1. So if you do this, for example, in n equals 4 weak coupling, what you get, if I again just draw a flat line like this, is you get a distribution which now looks like this. Here. And so it has this quite different shape. And so I just wanted to kind of go through the physics of what's driving each of the different regions. And so this object has very simple behavior in either of its, sorry, I can take like, let's say stress tensor or anything in the stress tensor multiplied. So most of this behavior actually won't, this behavior will be kind of universal, but yeah, so, but just for concreteness, one can take stress tensor. Good. So in either of these kinematic limits, it's quite easy to understand what is driving the behavior of this observable, because in each case, it's kind of controlled by a specific set of operators. And so in this limit, so physically, this is the limit where these two detectors are lying on top of each other. And this kind of Penrose diagram, you can think about it as these two detector operators which live at null infinity as kind of becoming very close to each other or kind of lying on top of each other. And so in this region, one has what is referred to as the light ray operator product expansion. You can kind of expand these. So you have some, again, I'll be very schematic. You have an operator product expansion where you can write this as some sum of specific powers, specific powers and some more general operators that appear in here. And And so in particular, if you're a weak coupling, then these are separated in their twist, and so there's a single operator which dominates. And you essentially just have a very clean power law behavior. And again, I won't go into it in more detail, but this just has some very nice power law behavior. And in particular, it's set by this twist 2, spin 3, and almost dimension of your theory, as was shown by Malacina. But at the very least, so it's set by some kind of low spin, or the enormous dimension of some low spin operator theory, and it gives this very nice power law behavior. And you can also notice that since this gamma 3 is positive, this is now an integrable singularity. So you can actually integrate it, and this will obey some rules relating it to the total cross section, but it does diverge. And so again, in the more kind of QCD or perturbative language, this is really a kind of limit of this DGLAP or kind of collinear physics. In the bulk of the distribution is where you just have to, or the only known way is to just brute force compute it in perturbation theory. And so if you just computed it in perturbation theory, some given order, it would give some distribution like this. And so at lowest order, this is just some very simple function like this. So it's just logs. It just has a logarithmic divergence on one end and a power law divergence at another end. And this is being computed to like third order. And so it has a fairly simple, it just has the alphabet for this is correctly something like this. So it has a pretty simple, it's just plug logarithms. And eventually at 3 loops, you hit some things that look elliptic, but it's quite well studied. And people have computed that to quite high accuracy. Then in this other region, you have physics, which is driven by the cusp anomalous dimension. And so this is kind of soft physics. And so again, the physical picture from the correlator side is this: what's happening is you're moving things, you're moving your detectors in infinity in such a way from your sources that they produce kind of or there's a kind of factorization, so they're all null separated, and this 4-point function factorizes into essentially a quadrilateral of Wilson lines. And so this limit, you can again write down a pretty simple formula for the structure of the shape here. And so again, the exact form doesn't matter, but I just want to show the anomalous dimensions that it depends on. If there's some integral, which is just resumming some kind of high spin objects. And so in particular, it depends on the cusp anomalous dimension. And what is sometimes, or this collinear anomalous dimension, which is just the subleading term. Like this. And so it's again has a fairly simple expression, but now you can see this proving very different physics. So this is the kind of high spin behavior of these twist 2 anomalous dimensions. And so you can see the kind of, or and the other kind of just fun kind of thing is, so from this, you can see that the resummation is actually strong enough that it plateaus to this flat behavior in this back-to-back region. There's actually so very long, it's a fun exercise to take the kind of, or compute the height of this using this formula. You can just do a saddle point approximation. So this was actually done by Parisi a very, very long time ago. And it has some kind of square root or non-analytic behavior on the value of the coupling, which is expected because in any fixed order perturbation theory, this thing just diverges. But when you resum it, it goes nicely to some plateau value. And so you can see that this is already just a very simple 2-point observable, but it has this very complicated structure. And in particular, it's kind of very nice for illustrating the different features of your theory. And so in particular, if you're an experimentalist, you can now go and you can read off, for example, this low spin anomalous dimension from the scaling behavior, or you can measure, for example, this cusp anomalous dimension. And so it kind of probes quite a bit of physics, even though this is just the simplest 2-point function. Okay. So now what I wanted to do is just to upgrade this discussion to QCD and to highlight what happens when you go from a conformal to a non-conformal theory. Are there any questions about that one before I go on?
Are the coefficients, is the like 1 over z squared 1 minus z, the coefficient of the logs? what you think of as the sort of, for amplitudes is the leading singularity. Is there a simpler direct computation of the 1 over z squared 1 minus z?
Sorry, you mean
The coefficient of the log.
this thing?
Yeah.
Good. So one loop, this is the actual full answer. So it's just that.
But I mean, for amplitudes, the coefficients of the logs are calculated using cuts.
Yes,
Is there some interpretation of the coefficients by, like, if I don't square the full amplitude, let's square cuts of the amplitude. Do I get 1 over z squared 1 minus z?
good. So I don't think you can square cuts, but I'll discuss it. So you can definitely take the leading singularity of the squared object with these constraints. And I'll show that. So this one is a bit more difficult to do on the full angle. So I'll show when I discuss these higher point ones, thereby I'll take a particular limit where it simplifies drastically, and then there's a much easier way of extracting these. So here it's not a particular, like you can write just into a representation and just take it, but there's not a clear, sharp way of kind of an independent definition, let's say, of it.
Just out of curiosity, is there a cousin of this object, a more supersymmetric something which would just be pure with no, just a log, no funny?
Not that's known. Yeah. Because so in n equals 4, you can of course consider like detectors in the multiplet. But the problem is these things really to converge, you need to have a sufficiently high energy weighting. So typically what happens is these other ones don't always converge. And so you get some kernels which diverge. And so it's not clear how to make, let's say, like a uniform weight object. And also so this is less manifest when you go to higher orders. One of the things that makes the function complicated is just because you have these kind of a very different structure in the logarithms at z and 1 minus z. And so it's hard to you can make one side manifest and not the other. And so in this, it's not known how to make such an object. So they'll become much nicer in the next section when I discuss these collinear limits. And so that's the kind of closest that one has. And there'll be kind of a leading transcendental piece, which is very easy to understand, and then some kind of trailing little bits. But for this, it's not understood.
And sorry, final question. These things are totally free of divergences?
Yeah. So the only thing that one has to be a little bit careful that they have. So when you compute the perturbation theory, they have these contact terms, and so they have like they're distributional. So this should really be plus, and then there's terms that go like delta of z and delta of 1 minus z. But these have finite, they're just some numbers that multiply them, but if you keep this, then everything's perfectly finite. And then they obey these nice sum rules, and so you can reconstruct these endpoints, and these are very important for doing that. But as long as you do that, they're completely finite. It's just they're distributional. Yes. Any other questions? Okay, then I will go on to QCD. So now I just wanted to highlight how this changes a little bit when one goes to QCD. Because this will be important because that's what you can actually measure in the collider physics experiments. So the main difference in QCD is that in these cases, it was always conformal. And so your theory that you're kind of probing or the physics is the same as a function of scale. And so the thing that makes the QCD result a lot more complicated is that depending on the angle that you're measuring, you should really think that you're probing your theory at different physical scales. And so in particular, in this kind of middle region, you should really think that you're probing the scale at the scale kind of q squared, which you inject into your operator in the middle. And then as you go in either of these directions, as you go to this 1 minus z limit, the scale that you're probing becomes q squared times 1 minus z, and ultimately hits the scale eventually lambda QCD like this. And as you go this way, you're actually probing the theory at the scale q squared z, and then ultimately you hit lambda QCD squared. And so in either of these kinematic limits, they're really IR limits of these objects. And so this makes a difference in two ways. So one, what you're essentially doing is you're probing either these Wilson line operators or these twist 2 spin J operators as you're kind of going along, these kind of flows into the IR in either direction. And so what will happen is there'll be some regime where you can kind of treat it just like this, but with some beta function corrections which are under perturbative control, and it will look the same, and then there'll be some, you'll eventually lose control completely. And so essentially what happens is that in this middle region, you have the same behavior as you would in a conformal theory, and this is because you can really compute this in terms of perturbative quarks and gluons, as the theory is asymptotically free. Then you get this nice scaling regime here where you maintain in perturbative control. And so in CFT, you would just go up like this. But in QCD, what will happen is at the angle where this hits lambda QCD, you just have a very abrupt transition, and it goes to this perfectly flat scaling behavior. And so this is why I use this example of this source with a bunch of things coming out. Is that in this region, what you should really think is you just have free hadrons coming off in your detector. So if you go to sufficiently, so of course it's not uniform over all angular scales, but if you go, what's happening is kind of clumpy, like this. And so if you go to sufficiently small scales, it's just a kind of bunch of completely free hadron. And so you can really see that very easily when you measure this thing. So when you go to the other limit, what happens is that you're typically, or in a nice world, you're in a regime where you have perturbative control over this turnover region. And so often what happens is you're able to kind of perturbatively go into this region, and then eventually you hit lambda QCD, but because lambda QCD is anyway just this flat behavior, all that happens is it doesn't actually change the appearance of this, and just kind of goes off again to z equals 1. And so it looks on this side very similar, and this side you get this very abrupt transition, which is really kind of the signal of confinement, or at least the presence of another scale in your problem. And so from this, you can really nicely extract, for example, the scale of what's happening. You can kind of measure that transition experimentally in some detail to understand kind of properties of that. And so, of course, in this region, there also, it has some effects, so it'll change a little bit the shape, but qualitatively, it behaves exactly like in the conformal theory.
Sorry, where's like Juan and Diego's kind of like spherically symmetric thing?
Yeah, so it's just.
But how is that? But I thought, so that dip down to zero, what happens to your dip?
The dip just goes away. The dip just goes away, yeah. Because there I blob so fast. So even though, so that's what one can kind of.
What happens? I'm just curious. What happens to the shape? As you crank up the coupling. But I thought you said that it has that. Oh,
it will just kind of flatten up into here. So something. So
the dip isn't at zero or anything.
No, the dip is not.
Okay, fine.
Maybe a bad.
Okay, sure. Okay.
Yeah.
Now I'm happy. Sorry.
Yeah.
I didn't understand. Okay, great.
And so what will happen? So this side has a pretty. This will just kind of come up to the flat.
Okay.
And then what happens here is that you no longer have a twist gap, and you just have some of them, and this will kind of collapse in and just.
That flattens. That's still
just
flat.
kind of completely flat. Yeah.
This area where Higgs is kind of confining, what
Yeah, so if it's Higgs instead of confining, so then you can just actually compute it. So you can just put some finite masses, and you'll find it has essentially the exact same shape. So it changes a little bit. So you can, even in QCD, you can compute kind of the leading fractions that go like, let's say lambda or lambda QCD over QZ. And so will have a little bit of, these will depend on whether your theory is like Higgs or confined or something. But in a first approximation, it will look exactly the same. And this is just, so essentially any scale you put in, you'll just detect it there, because it's just interrupting this nice kind of conformal scaling. Yeah. Perfect. Any more questions about this? And then I just want to say the one other thing which will be important when I show the plots later is the kind of region where you can where you can kind of reliably, perturbatively compute things in this nice scaling regime is this region in here, where what you want is a Z very, very small, but you also want it much, much bigger than lambda QCD over Q squared. And so this is where you can really benefit from these very high energy colliders, so they actually get you into this regime where you have this very nice conformal scaling and can measure higher point correlation functions over a very wide angular regime. And so that's really the benefit of, for example, the LHC for studying these objects. Okay, perfect. Okay, so now what I wanted to do is, are there any more questions just about this or the kind of physics of what's going into this? If not, then I want to discuss a little bit about these higher point correlation functions.
Sorry,
Yeah,
could you please tell me a little bit about around what kind of region we can still trust factorization for energy and indicators?
so it depends what meaning of factorization. So say even still in here, you can trust the overall factorization. It's just you can no longer compute it. So you can still factorize this into some hard component that produced it, and then some collinear factor which is describing this. It's just that collinear piece becomes non-perturbative. And so this piece is still kind of completely universal. It's just you don't understand it. And same as on this side, you're deep in your factorization, you understand it perfectly. It's just that it's now non-perturbative. And so actually one fun thing that we can actually do now is because here we have this factorization onto this Wilson loop, they can actually now compute the dependence or this Wilson loop on the lattice. And so we can actually match our perturbative calculation right onto a lattice thing and continue it out. And so we can actually the factorization is holding very well. It's just you've lost perturbative control.
That means that do you need to upgrade the factorization?
No. It's just some component, some function that appears in your factorization has just become non-perturbative. And that's common, or that's true in almost all factorizations once you push them into some regime. And that's in some sense the power of the factorization is that you have a universal non-perturbative object, which you can understand. Okay. So that was just an overview of the type of physics. So now what we'd like to understand. So hopefully that convinced you that, at least from a physics perspective, these allow you to probe things in a nice way. And so now what we'd like to understand is just the analytic structure, for example, of higher point correlation functions. And this is where, from a kind of integral perspective, these things start becoming a little bit more interesting. And so what we'd like to understand is just generic endpoint functions of these objects. And so the first thing which one can try and do is to just compute these for completely generic angles, just on the sphere. So you could just take like this, and try and compute these objects. And so these are just then functions of the angular separation between these. And these are very complicated objects. First of all, because you've largely broken all the symmetries of your problem by putting this time-like source. And second of all, they're very dependent on the particular source which you happen to choose. So they're nice, but they're very complicated objects, and they're a bit hard to understand. But there's a limit which one can take, which both drastically simplifies the integral structure and is also what you actually want in high energy colliders, which is the limit where all of these detectors become collinear, but you keep the cross ratios between them finite. And so in this limit, what happens, so what you want to do is to take all the Zij to 0, but keeping their ratios fixed. And so what you can imagine is some nearly on-shell source, which is decaying into some particular configuration. And so this will now have some energy correlator where it will be some function, for example, in the 3-point case, of some particular variable. So you can kind of move out a scaling variable, and then you just have to compute the shape dependence. And so just to go through why this becomes such a nice object. So there's two reasons. So one is that the phase space drastically simplifies, and the other is that the object which you're having to integrate becomes what is called a universal splitting amplitude. And so this becomes both much simpler from an integral perspective, and it decouples from the particular source itself. And so just to see what this looks like, so if you wanted to compute the endpoint correlator, so it is this ENC like this, and one just wants to do it at the lowest order, which is where you just excite each of the detectors. And so you don't have to integrate over anything going in other directions. Then what this object is, just as a very concrete integral. So it's just an integral over, you can think of them as the kind of energy fractions of these particles. And so the phase space is essentially reduced to this kind of canonical simplex. So that's a very, very nice thing. You then have some energy weighting, which comes from the detectors themselves. And so if you work out the phase space, it's just a factor of the product of all their energies squared. And then you just have to integrate this against this 1 to n universal splitting function. And if you're just doing this for the lowest one, this is really just a tree level object. And so this object is the splitting function, so it's the splitting amplitude squared. And so you've simplified your life drastically, both because this is a very simple integration region. And this is just some universal function, so like an n equals 4 or whatever, it's just something you can get. And also this is just purely a rational function. So this is quite a simple object. So this is now being computed by, for example, Song-He's group up to, I think, like 12 points. So it's known very, very accurately. But just to give a sense of what these actual integrals look like.
What is square in the parentheses?
Sorry.
What is square in the parentheses?
So you get the one factor from the energy weights,
Yeah.
and the second is when you convert the integration region from Mandelstams to energies, you get another factor, and so that it just ends up being squared. And so what these, I won't write them down explicitly, but the kind of types of things you have, so they just have denominators which are products of a bunch of Mandelstam. So they could be things like, and sometimes sums of energies, for example. So things like this. And so you just get a bunch of these. And the very nice thing about these is if you write these in terms of these integration variables x and the detector differences like this. So these, any Sij is just xi, xj times the length between these 2 points. And so you can see that essentially what this object is, it just has a bunch of quadrics in the denominator. And so this gives a very concrete integral, which one can then try and study. So it's essentially, it's kind of like a Feynman parameter integral of a bunch of quadrics. And so one can then try and explore the structure of these observables. How much time do I have?
15 minutes.
Okay, perfect. Okay, so what I want to do is just say a little bit what is known for the 3 and the 4 point, and then I can just show you some pictures. So as before, so the generic endpoint function was computed at strong coupling by Malacina, and then they just had not really been explored at weak coupling, and so we just started computing them. And so what's known so far, so what is known? So we've explicitly integrated the 3 point. And so this one has been done in n+4, QCD. And now we have it actually in gravity as well. And then we've also done the 4 point, just in n equals 4. And then at the integrand level, there's now a known integrand for this up to, I think it was 11 or 12, but I'll say 12 of these objects. Yeah.
Is there any new physics by going up to higher point that you didn't have access at 2 point just to motivate it?
So it depends, like, do you mean from an actual, like, let's say collider perspective or from like exploring the functions perspective?
Actual collider perspective.
Yeah, good. So there's some very concrete, yes. So there's a number of different things. So the 2 point function, essentially all it can do is identify a scale. But then what you want to see are kind of the dynamics which happen at that scale. And so if you want to understand, let's say like the quark gluon plasma, if you just measure this 2 point function, essentially what you see is the size of the quark gluon plasma, but it tells you nothing about it. And so then what you want to see are like the kind of shape of it. And so then at that scale, you measure like 3 point, 4 point, 5 point, just like in cosmology. Also, from the perturbative side, there's a kind of target of these is like the top quark decays into essentially a 3-body decay. And so if you can try and measure its mass very precisely by this understanding, so that's a very like sharp thing of just perturbatively understanding the 3 point function gives you access to the top quark. And so, yeah, I think the 3 point definitely, 4-point and beyond, I don't have a sharp physics motivation, but I'll show you like a plot and it looks fun. Yeah, but the 3-point, there's definitely a lot of particularly in the kind of quark gluon plasma, there's a lot of interest in using this to actually understand the structure.
4-point accessible experimentally.
Yes, I'll show you a plot of the 4-point. Yeah. Okay. Yeah. And so these have a very simple structure. So the 3.1, I'll just write down it's a very simple actually integral, and then I'll just state its properties, and the 4-point I'll just state some of its properties. So for the 3-point, I'll just do it in like 5-4 theory. So the way that one can think about this is you're really constraining some particular shape on this surface here. And then you have some splitting, which kind of comes in if you're in 5-4 theory. And then because it's squared, these kind of go out like this. And so the integral that one has is really just this factor x1, x2, x3 squared, sorry. And then you just, all that you have is a squared propagator, so just this happens to be squared. And so this is a very concrete integral. You can just stick it into some program you're liking, and n equals 4 won't be a very different integral. But so it's very easy to analyze, for example, the properties of this. And so you can see that what happens is it has singularities in the physical region, which are just the OPE singularities. So they're just when either z to 0 or z to 1. And so there it just factorizes onto a 2-point function. So these are very easy to understand. And then you also have singularities in the unphysical region. And so this in particular is when z goes to z bar. And so this is when you get into this kind of collapsed or flattened triangle region like this, where this thing kind of collapses down to here. And so here, I don't have as good of a physical intuition for what's actually happening. But if you work through, this is coming in a regime where you also have this x1 plus x2 equals 0. So it's kind of as if you're kind of removing the source which created this object. And so there should be some nice kind of interpretation of these objects. So this is something that apart from mathematically, we didn't kind of expect before from standard kind of QCD type factorization, but it seems to be a generic feature when you go to higher point functions. And so it'd be interesting to understand or to explore these more generically, how you factorize onto these in this kind of analytically continued kinematics. So we also computed the 4-point function. So this is a much more complicated object. And so again, I'll just go, so again, it happened to be, so it's way, you can express it all in terms of weight 3, point logarithm. So you can just brute force do it. At least in n equals 4. And so here it now has physical singularities. So I won't obviously write out the full answer.
Is that 3-point guy the Rogers dialog?
Yeah. Or so it has both so this has both this like Bloch-Wigner. So this one's just a Bloch-Wigner. Yeah. But there's also, in the Rogers, so this has, so in like 5-4, if you only have like in 5-4, it's just Bloch-Wigner. If you go to n equals 4, you also have terms which are kind of linear, and these are from like Wilson line kind of limits essentially. And so these give something which is not the Bloch-Wigner, it's actually much more similar to the Rogers. So it's, you get a few extra terms from Wilson line, but it's still very, very simple. Yeah. So these are very, very concrete things to play with. And so in the 4-point, you just get some physical singularities. So again, these are just in particular OPE limits. You have someone kind of a 2-particle OPE limit. You now have a 3-particle OP limit. And then you get a whole bunch of unphysical singularities, or these are these kind of total energy singularities, which are not accessible in the physical answer. But these are, for example, when you have some triangle like this, you can then have some thing which collapses down onto it like this. Or you have singularities where, for example, 4 of them lie on a circle. Like this, and so these are the kind of analogs of these total energy singularities. And so again, something like this, there should be some nice factorization of how this works, and this is something which is not being explored in the Yang-Mills or context at all, but it would be interesting to understand because these give a lot of information about the structure of the amplitudes. And so I should just say again, the kind of complexity where these start to get quite nasty is because these are quadrics. When you start going to higher orders, you have to simultaneously solve a bunch of quadratic equations. So in particular for this one, you get things where you have to solve simultaneously some kind of hyperplanes and multiple quadrics, and so these intersect in some cubics, and so these roots of cubic or these cubic roots appear in the leading singularity. And so just for fun, so in Solomon's paper, he gives one that you have if you want to compute the 5 point. So we were kind of lucky that we stopped at the 4 point, but you get some very complicated. Which gives some like 6th power equation, which enters your leading solution. So things start to get quite complicated quite fast, but there should be some nice, there's now a lot of, or there should just be some nice at least understanding of the singularity and stuff, or if these things obey Steinman relations or a bunch of interesting stuff.
Is there some, at zero Thora, some analog of Coulomb Norton?
No, I think there should, this I think is a very simple thing, which one should just sit down and write down, and that'd be very fun to do. And now that there's all this nice data, one can check it up to 12, and that should be, and one expects that it's these pictures of vanishing total momentum, but that'd be a very nice thing to do. Yes. And so I think for time, so I'll just say, so we've also computed this in n=8 supergravity. I won't, so we computed the 3-point function, and so it again has a very nice structure. So you can compute both the full angle 2.1, and so this is kind of interesting because in n=8, you have very tame collinear singularities, and so you don't have a pole in the collinear limit, but you still have these nice functions of the cross ratios, as you still get, it's actually expressed in terms of the same set of functions as the n=4 one. But our hope, and so we're still kind of simplifying it, is that in this n=8 case, or it's kind of supposed to be very simple, and so it's in a kind of another place where we can explore these. And the other thing which is very nice for us, and then I'll show the pictures experimentally, is that so in n=4, we relied on having all these nice splitting functions, which we could integrate. And so in n=8, so what one wants to do is to have 2 things collide and produce a kind of whole bunch of gravitons on which you measure the energy correlator. And so what you need is the kind of spin-summed cross-section into n gravitons at n=8. And so these are very hard in n=8, but fortunately, Zvi and collaborators have computed these like 6-loop or something like this with the complete spin sum. And so one can just take the cuts of these, and these are exactly what one needs as integrands for energy correlators. And so
Aren't these collinear splitting things just products of 3 points?
they're just,
Way?
yeah, I think so. We can also do it from that. Yeah,
You don't just square those, right?
yeah. And it's just nice. So they've, like, you can just square them, but doing the state sum
I understand,
is,
yeah.
And so,
But you should be able to start from that.
yeah, so that's how we did the lowest ones. And then we've now, to go to higher points, it's just they have it all sitting there fully squared over the multiplet. At lower orders. So we also computed just the 2.1 in pure Einstein gravity. And so there we just squared and deal with the state sum.
But so the basic object you care about is 2 to n mod squared
Yeah.
spin sum.
Yeah. And it's just convenient for us that they have done all those, they developed all this technology for doing those spin sums, and so we can just reuse those. And so yeah, if I have about 5 minutes, I'll just show quickly a few pictures, just to show that these are kind of real.
It's funny you said like in cosmology, because it's a little bit the other way around.
Yeah.
Since we haven't seen.
Yes.
any of them.
That's right, these are not really well prepared, but these are just to show some of them. So just the first.
You're recycling slides for us.
So just the first thing to say, just very briefly, and I won't go into detail, but there's a lot of different experiments for different purposes in both the particle and nuclear worlds. And so in the last year, they've actually gone and measured these energy correlators in almost all existing collider systems. So in E plus E minus, proton-proton, proton-lead, and in lead-lead. And so there's a huge experimental program to measure these. And so the only other type of collider that I know of is electron-proton. And so people are reanalyzing this to do this. And so the simplest case, which is the one that I discussed at the beginning, is just where we have a local source. And so this is something we can do in E plus E minus colliders. And so this is just a fun history slide, but this is actually the first ever measurement of the energy correlators. So in 1980. And it's kind of fun because it has the actual calculations. So Veneziano and collaborators first understood how to resum this collinear limit or small angle limit, at least at leading log. And Parisi understood how to do the back-to-back. And then they combined it with this Basham, Brown, Ellis, Love, and this is kind of the first, like, that I'm aware of, resummed event shape calculation. And it's compared with, so this Monte Carlo thing is this Feynman field, very old school model. And you can see that you kind of get this qualitatively the shape which I described before. There's not great agreement, so like there's qualitative agreement, but it's not great with the theory calculation. And so one thing that we've actually done, so motivated by all this nice stuff, is we've gone, or the theory progress is we've actually gone back. So all the Aleph data actually exists on a hard drive. And so you can go back and we've actually reanalyze it to remeasure these things. So this is with a group led by Yanji Li at MIT. So they've done a lot to actually like dig this out and understand how to use very old code and stuff. And so just for fun, so their entire data set is 28 gigabytes. So for $8, you can have your own version of it. And you can really just, it takes like a second to run through it. It's quite remarkable how much these things have changed. And so I won't go into detail, but both on the experimental side, there's been obviously huge advances in computing and unfolding and these types of things. And so we can do a huge amount better. And so on the theory side, because of the kind of outgrowth of these detector things, we can now do calculations on tracks. And so you can use very, very, very good tracking resolution. So that will really, or that really does help. So just to show, so this is done by this MIT group. So this is the actual data of this 2-point correlator, which kind of showing these regions, which I described at the beginning. And you can see, obviously, compared to what I showed those plots before, you have just this incredible resolution down to like 10 to the minus 4. And so you can really very nicely resolve all these different kind of scaling regions, the transition regions, that you really do get these exactly flat hadrons. And you can do it in really like excruciating detail compared to what was done before. And then I'll just show, so it's a bit hard to see in this, but this is our kind of calculation of this object using, it's the kind of massively upgraded from the Parisi et al. Calculation. So this is their kind of old one, and so this is the new one. And so this is starting, so this needs to be upgraded a little bit, but this is now getting into, so one is in this region in particular, one is using kind of 5-loop and 4-loop information. So one is really pushing it because you understand exactly how these factorizations work. You can really use these kind of state-of-the-art QCD things and get very, very precise understanding of these objects.
Which was the old theory?
So this is a combination, so this down here is the old theory curve. So this is a combination of Parisi on this side, and then Konishi and Veneziano on this side. And then this one that actually works very well is this Feynman field Monte Carlo. So it is not something I'm familiar with, but it seems to work quite well. Yeah. And then this in the middle is just the 1-loop calculation of Basham, Brown, Ellis, and Love. So now this is down to, in here one has like 3-loop.
But what's the excuse for it being so far off? Alpha log squared isn't that big.
But yeah, but the problem is here, this is also 7 GeV.
Wow.
So it's yeah. And you do, so one thing which I didn't go into, but for numerical, so even in this middle region, even though it's perturbative, you do get corrections which go like lambda over Q. So like non-perturbative corrections. And you understand, so there's old work added by Kortensky and Sturman, where you can exactly understand the functional shape of these leading corrections. And so these end up being numerically important for actually getting qualitative agreement.
And over Q is still 10%.
It's 10%.
Why is it so far off?
It's, yeah, I mean, they end up being kind of numerically larger than one might expect. And also, I mean, or just as another, so when you actually look at the structure of the perturbative QCD corrections, they're very large. They're just like numerically, they're extremely large. And so this thing actually converges quite poorly. So it has like so it's very symmetric, and so it has quite large, they're almost just like flat jumps.
What would the unfancy computation have looked at 90?
So it's low down here. It's still very low.
Oh,
It's low in the center. It's a bit hard, yeah. So it's still quite off, actually. And you really need to push the perturbative accuracy to get into that regime. And this is just because so if you do it in like QED, even if it like forgetting the fact that coupling is small, but just because you don't have all the color factors, actually it converts very nicely. But in QCD you just get numerically like huge coefficients in each order. And so one has really had to like turn the crank to push these things to quite high orders.
and these track operators are
Yeah.
just like putting them along the track, putting what did you mean by the?
Good, so you have to, yeah, so if you measure something that's not, so if you measure the total energy, so when you're actually measuring things at infinity, there's a kind of interesting property, or it's kind of obvious, but you're really always measuring these detectors on half, right? And so you have to, in general, do a matching between an IR detector and some UV detectors. So you should really always think that you have your like, or just in general, if you have your detector, this is what you're always actually measuring. And then generally you have to match it onto some, what sometimes calls these like, they're kind of like Wilson coefficients, but now you're going from the UV or from the IR up to the UV. And so you have to match this onto some UV detectors, which for these are in terms of like quarks and gluons that you can do the OBE in terms of. And this in general introduces some kind of RG. And so in the case that you have, let's say you measure tracks, so this is asking some property about the actual spectrum of charge hadron. And so it's not something that's computable purely in perturbation theory. And so before people have this classification of kind of like either infrared and collinear safe or just not. And so now there's a kind of more refined view where it's whether or not one can easily understand the mapping between the detectors in the UV and the detectors in the IR. And so typically it turns out for things, if you're measuring, let's say, energy flux on a specific set of particles, like let's say charge or specified by some property, you're at a high enough, and I can go through in more detail, but you're at a high enough spin in these two Fauci plots that the map is actually very easy. And so what you need is some non-perturbative function, which are called detector functions or track functions, but it's really just a number. And so if you just, it's actually very easy to understand to lowest approximation. If you just think of the pure energy detector and you want to measure it on tracks, if you just measure the 1-point function, all you need to know is the first moment of it, which is like the average energy going into charged particles versus not. And this is just like 0.6, like it's just 2/3 piles of charge versus not. And so then you need higher modes of these for higher like, kind of contain the fluctuations, but you essentially need these what are called detector functions. And we now, from understanding better the properties of these detectors, we can very efficiently, like we can compute things at whatever end loop order, but then also include this wrapped into them. And so this is very important to be able to have this kind of very nice or very, very, very fine precision. Also the LHCs, we really understand how all of these behave on subsets of particles. And so this is
the point that you can measure all the particles that come out, but only a subset.
the point is that you get much, much better resolution if you restrict to these particles. So you can, in principle, measure all, but then you're really using these like hadronic calorimeters, and there they have terrible angular resolution. Whereas these are really these nice like silicon detectors, and so you have like really incredible resolution. And so to be able to, especially, well, hopefully show in a second, these like higher point functions, these are just not possible with the like hadronic calorimeters. And so you really need very precise measurements, and then you just throw like some, you can also add the other ones in as an average and give them less weight, but it's nicest to just restrict to these ones that you have very, very good angular resolution for.
Which ones?
The charged particles. Yeah. And sorry, just to quickly show two more plots, then I'll finish. So just to say, so when you go to the LHC, so now this is, you have to use much more computing power, but you actually get just these extremely high energy jets. So this is now a kind of zoomed in region of this very small angle behavior. So this is where you expect it to get this very nice like power law scaling that goes like 1/z to some enormous dimension. And so you can see if you kind of compare the angular scale where it's kind of doing nicely in these very old plots, it's kind of entirely blown up, and so you get this you can really focus in on these regions where you just get beautiful power law like scaling. And so by measuring these anomalous dimensions, I'll just skip it, by measuring these anomalous dimensions, even though this is just a very preliminary thing, you can actually get competitive extractions of the value of the strong coupling constant. And that's just because you have very nice theoretical understanding of these objects. And so this can definitely be improved. This is just kind of a preliminary thing, but compared to these other things, which are, let's say, 3 jet mass or something, these are just under so much better control that you can really hope to push them. And so then just to show pictures to illustrate your question, so you can also just go and measure, for example, 3-point functions. So this is the non-Gaussianity, so it's normalized to some 2-point functions. But you can see it has this nice kind of equilateral, this kind of flattened, and then this squeeze here. And then you can start going crazier, and so you can actually measure the 4-point functions. So these become harder to visualize. And so what one has done is one has fixed these 3 detectors, and then you move this one around and make like a heat map. And so you can see that it becomes hot as it comes to either of these, and these are just the 3 OPE singularities. And it has some generically just more complicated behavior. And this is just the analytic plot of what it looks like in n equals 4, just for comparison. But this is just to show that they can measure. So these are getting now, this is, at least for me, kind of fun, because this is really a 4-point function which you can just play with, and it has all these nice properties, and they can really kind of measure these things and have put a lot of effort into developing techniques to kind of measure these things very nicely. And they're also doing these in kind of heavy ion and stuff, but I'll skip that, and so that's it.
We're seeing a lot of questions in the talk. Should know before we go get some cookies.
Can I ask a question? So maybe it might be ignorant because I'm an experimentalist. So on the plots you showed from like LF data and stuff like that, so I'm a little curious, maybe I can press a little on like what you hope to expect. So to me, it seemed like you're essentially probing depth of structure, these energy point correlators.
Yeah.
And like for this plot, for instance, I guess my naive interpretation would be like you're essentially just representing like the entire Z cross section like at a Z pole in a different form. But I guess I have a couple of questions. So one, like first, when you just define your endpoint correlation function in terms of theta, are you not losing information by like projecting onto this only the theta plane versus some sort of like theta as a detector versus phi? And my second question would be, so up until now, I think what you spoke now, like 3-point, 4-point correlators, I understood those to just be within the context of a single jet, or like a hydrogenation process, but have you considered putting together like 3-point correlators together with 4-point or 2-point to actually like represent a multi-jet event?
Yeah, good. So for the first one, so you're definitely losing some information by projecting down. Like, so we're just looking at one projection, but it's one projection that we have very good theoretical control over. And so you can think of it as building up from, as you said, the simplest thing you measure is like one number, which is the cross section at the Z pole. The next thing you can measure the 1-point function, which just has some angular distribution. And then this is the next simplest thing, but you can definitely to get the full information, you need 3-point, et cetera, et cetera. And so there's a number of different things that one would like to extract from this. So one is just, if you're very pragmatic, you can try and just extract the value of the strong coupling constant from this. So this is one of the most now precisely computed observables. And so one would like to extract the value of the strong coupling constant. There's a bunch of kind of non-perturbative parameters associated with QCD about this turnover, which are also interesting to nuclear physics people. And the other thing which we're interested in is just the kind of convergence of the properties of this behavior, or in the simplest possible E plus E minus system, and then moving it to the LHC. So you just want to understand it kind of very, very well in this simple system, and then you can start understanding it both at the LHC where you already do, but also in more complicated like heavy ion systems. And there you just want a very, very clean baseline where you can compute everything, you have everything under control, and then you look for deviations. For your other one, so at the LHC, it's largely a pragmatic thing where you want to take n correlators inside a single jet, just because there you don't have control over it's just, yeah, the geometry is much more complicated, it's sensitive to the initial state. And so if you factorize onto this single jet, then you're not using any properties of the jet itself. In fact, you're throwing those out because you don't want that. It's just that it's a way of kind of isolating these very high energy collisions, and where you just have like n particles. So it's just a way of extracting something universal, which would be the same in E plus E minus as there. And so here we can really measure it as a full function of angles on the celestial sphere, and that's a very complicated, so they will also measure the 3-point functions as the full function. It just becomes that's a complicated, so like 3, it's, you can do it, 4, just, I don't even know, you need some motivation to do that. And so that's kind of correlating things, like in particular, this back-to-back region, it's a way of, it's like correlating things in different jets, but without having to define jets. And so that's the much nicer way of doing things. And so in these, when it's really E plus E minus, you can do it over the full sphere, and it's a very nice object. And then it's just in these other colliders, we're restricted to these specific angles where we can understand them nicely.
Thanks.
Yeah.
Yeah, I have a really naive question. So polylogarithms famously have very interesting monodromy. What's the physical interpretation?
Good. So yeah, that's a very good question. So for these ones, like this 3-point function, it actually evaluates to a single valued harmonic polylog. So single valued polylogarithm. So this is this particular block linear. And so it's single valued in the real region. And so here, when I kind of said this function of z and z bar, I'm really by meaning like z bar, I mean like the original z star, or like its complex conjugate. So you can then free it to be a function of like z and z bar. And so then this is something which is related to these unphysical or not on the physical sheet singularities that we would like to understand better. And so these already have very interesting, so if you study, for example, the monodromies about 0 or 1, so there's this Lorentzian inversion formula for the like 4-point function of local operators. And so because kinematically this object behaves exactly like the 4-point function of local operators, you can also use that here. And so you can use these discontinuities or monodromies to extract the kind of information about the particular operators that are appearing in the OPE, for example. And so so that's kind of one way in which you can use that. And so, but I think generically we don't, so particularly if these higher point ones, we would like to better understand their behavior on other sheets. And it seems that they have very interesting singularities, which largely dictate their properties. And so for those, like, I don't have a physical, so in particular for these 0, it's like these ones where you like collapse like this, or like for example, onto here, these appear, these are coming once I continue around, and I don't have, so like these OPE limits, I have a very clear physical limit. They're just like collinear physics. I understand it from the standard gauge theory perspective. This factorization, I don't have a clear physical picture. I think it'll be interesting to understand better how things factorize on these other sheets for these observables. And I think that's just something that has not been explored. We didn't have data before, theoretical data before now. And so now I think that's what we have, a large aspect of what we'd like to investigate.
And for n equals 3, is there an interpretation of the 5-term relation on the dialogue?
Is there an interpretation of?
So the dialogue
Yeah.
satisfies this famous 5-term relation.
I don't know if there's an interpretation in terms of this, so it makes the calculation much simpler. Because here you sum over permutations of the detectors, which are exactly summing over those permutations. And so it makes the final answer very simple. Because when you do it, the particles can go into any of these, like the detectors are bosonic, and you really have a sum over all the permutations. And it literally has, this thing has exactly the symmetry group of that, and you just sum over all of those. And it just means they're all written in terms of the same, it makes the final answer very compact.
But I think the point is that your actual object is sort of manifestly the volume of the hypersphere.
Exactly, yeah.
So the 5-term identity is just ways of cutting up that ideal tetrahedron in different ways. The full physical object is the actual volume direct.
Yeah, it's the sum over all those permutations, yeah.
I guess another aspect of Greg's question is that we don't have the full analog of the optical theorem for these energy correlators, right?
No.
We don't, so that's, if we did, then we would, for amplitudes, we know, for example, at least at one loop, we know every single discontinuity is moving some trees together in some way.
Yes,
But we
and
don't
that
know
would be
the
very
analog.
nice to understand for these out there. Yeah.
I have a final quick question. What about like, not energy, but baryon number, charge,
Very good, so
those guys, yeah.
very good, yeah. So this is partly, I was gonna talk a bit more about these more general detectors, but we've understood, so if you just measure like charge, let's say, this is so screwed up by hadronization that you essentially get nothing interesting. And this is now understood from this more kind of modern perspective of these kinds
Something
of.
interesting, that is zero, like it's basically the
Well,
net charge is
it's
equal to
essentially like
zero?
no, or let's say it
Oh,
doesn't,
yeah, I see.
it doesn't preserve any of the underlying perturbative structure. And so the questions that seem to have very nice answers, or if you do, let's say, you can do something like energy times charge. And so because this thing has still an energy weight, or like energy, let's say on positively, so one thing you can do is like correlate energy on positively charged particles with energy on negatively charged particles.
So in other words, you could, if you try to measure charge, very soft particles or.
Yeah,
Exactly. And so you want to stay,
Yeah.
well up above this.
But what
So
about
then-
baryon number? Baryon number should be a little better, shouldn't it?
But it's still, you just have soft baryons.
Oh, really?
And so you can do like energy on, let's say, if you do like energy on protons, energy on pions or something, that will actually behave relatively well. But once you really drop to having no energy weight, then it really disturbs it.
Sorry, aren't there like 20 hadrons and z decays or something like that? 20.
But then you just don't have control over it. Then it's really like, once you're limited by the number, right, then you're really like sensitive to the properties of that atom. So you want to be in a regime where you can freely produce them. Otherwise, you're kind of sensitive to the.
Oh, this, in order to be able to compute it.
To compute it. Oh, yeah.
Oh, I'm sorry. I got it.
Yeah.
Now,
No,
But they're sensible. I mean, they're in principle.
Well, they give something.
But you can't, yes.
Yeah, but for these, we've been able to understand, so let's say you do like E plus and E minus, you can actually compute these and see the variation, and it gives like a small deviation. You can see that like, even from the, like it's not electromagnetic, but just from QCD dynamics, the plus and minus like to be more together than like, let's say plus and plus. And if in some string model, this is kind of what you'd expect. And so for these general types of detectors, we now actually have pretty good theoretical control, and they can measure them nicely. And so when it's kind of starting from the ones that one understands and then broadening. And at some point when you want to keep, it's kind of energy flux on subsets of particles, which seems to be a question which it has a nice answer to, yeah.
I'm still a little, I mean, the charge I understand, because you're like, you know,
Yeah.
I plus, I minus all over the place, but baryons are a little bit.
So they do something, it's just one can't compute them,
All right, any other questions for Ian? All right, if not, let's thank him again for a wonderful talk.